So, we've reached the end. No more pure logic after this, unless you ask for it. At various points in the study of logic, students lose sight of how all of these P's and Q's, inference rules, and so on actually hook back up to reality, English, and actual arguments. So I'll give a couple more examples in English. If you look at this first argument, it could read, if the burrito is in the first bag, then the taco is in the second bag. The burrito does, in fact, happen to be in the first bag, so we can infer that the taco is in the second, if these premises are true. And that's what matters in pure logic. What will actually be true given a set of premises, claims, or beliefs. Logic is our tool for reasoning correctly. Everything else may be questionable, but with logic, at least we can reason certainly about those questionable things. So, to continue with this example, since I can see it follows that Q, the taco, is in the bag, I can conclude further that it's true that it's in the bag or anything else is true, however empty that second disjunct may be. I'm only asserting that one of the disjuncts is true in a disjunction. That may seem cheap, but we can't help the rules of inference any more than we can help the rules of addition. We can see that 2 plus 2 must equal 4. So, given that it's true that the taco is in the bag, I can logically conclude that it's in the bag, or I'm a monkey's uncle. In this second argument, we're going to use a classic form of refutation called the reductio ad absurdum, which is a tool used to reduce a proposition to absurdity. What that means is, if you assume something is true, and that assumption leads to a contradiction, you've shown that that assumption is wrong. So, let's say there's an argument about whether or not God exists. Here I'll use Teller's convention of using variables that remind us of the argument's semantics. So, we reason that if God exists, then God only wants good things. And if God only wants good things, then evil shouldn't exist. But in our discussion, one of us is saying that God exists and evil exists. So, to use the reductio ad absurdum, we'll assume, in light of these premises, that God exists. And then we'll think about what that means in terms of the premise, if God exists, then God only wants good things. And if God only wants good things, then evil doesn't exist. So we can conclude from these premises that evil shouldn't exist. And then we have to think about that in light of the premise that God exists, but evil also exists. So we can simplify that premise that God exists and evil exists to evil exists, which gives us the conjunction evil exists and evil does not exist, which is absurd. We've reduced this to absurdity. And absurdity being a contradiction, which is logically impossible. So, if we assume that God exists, we arrive at this contradiction. Since we arrive at a contradiction, we can conclude that God does not exist. Of course, there are counter-arguments to this that I've covered elsewhere in topics like philosophy of religion. But let's move on. I hope those examples help to show some of the value and purpose of studying pure logic, and how it's paramount to all forms of reasoning. Let's look at a couple more examples of natural deduction without semantics, so I can demonstrate some more rules and explain the thought processes and strategies you can employ when analyzing an argument logically. So, the goal of this argument is to prove R or S or T or U is a valid inference. What we should notice off the bat is that this is a disjunction, and that some of the disjuncts are not present in the initial premises. So, we can safely conclude that disjunction introduction might be used a couple of times. Further, we can see that line 2 is a conditional, so some sort of hypothetical syllogism might be used also, like modus ponens or modus tollens. Further still, we can see that the line 1 premise matches the replacement rule De Morgan's, but the conjuncts are in the wrong order, so commutation might be necessary. So recognizing all that, we can get started. Since we want to reorder the atomic statements or the conjuncts of premise 1, we can use commutation, and then to make it identical to the antecedent of premise 2, we can apply De Morgan's law. Once we have the antecedent, we can conduct a modus ponens using premise 4 and premise 2 to give us R or S. Since we need the atomic statement T, we can introduce that with a disjunction introduction. And then we can apply the associative law to line 6 to give us R or S or T, which is exactly what we need for the first disjunct of the conclusion we're aiming at. And then to finish it, we can surround line 7 in brackets to show that it's a complete statement, and then use disjunction introduction to give us the conclusion we're aiming at, showing that it's a valid inference. For this argument, we can see two things from the outset. It's a conjunction overall, and it contains disjunctions with one atomic statement that isn't present in the initial premises. So, using your critical thinking skills, what does that mean? If you're thinking that it means there'll be a disjunction introduction at some point, you're right. You may have also noticed that there's a modus ponens available. A modus ponens that can give us the last conjunct we need for the conclusion we're aiming at. So, reasoning backwards from the conclusion, we can see that our last move will be a modus ponens on lines 1 and 3. So let's get started. We can simplify premise 2 to R, and then, using premises 1 and 4, we can introduce P and R by conjunction introduction. Using premise 5, we can introduce the second disjunct that we need for the conjunct of the conclusion we're trying to prove is a valid inference. So we can introduce S and T using disjunction introduction. From there, we can use premise 1 and premise 3 to conduct modus ponens, deriving Q. So now we have everything we need to use conjunction introduction again to give us the conclusion that we're trying to prove is a valid inference. Now, finally, we can get to the chapter. This section is about solving derivations. The first step is becoming comfortable with the rules, not just memorizing them. We need to become familiar with their applications to the point that we can comfortably read them out loud, apply them, and anticipate future moves. Part of this is being able to identify logical moves you're making in your quotidian reasoning. This isn't easy at first, but if you practice enough, you'll get there. In your coursework logical reasoning, at least in a pure logic class, you'll have the benefit of semantic-free arguments with clear conclusions to aim at. So, take advantage and reason forward from the beginning to the end of what's available, and backward from the end towards the beginning. Teller gives a nice, simple example to illustrate his advice for attacking derivations, and I'll repurpose his example to explain my own. But be sure to read what Teller has to say about these examples, because you never know whose insights are going to be more valuable to you. Look at this example. You can see the premises at the beginning, and you can see the conclusion you are working towards at the end. Start by asking yourself, are all of the statements I need for the conclusion present in the premises? If so, think about what inference rules or replacement rules you could use to free up those statements. If not, you can look at rules that have the power to introduce statements, like assumptions or disjunction introductions. In this case, we see that both of the statements we need are in the premises, so let's think about rules we can use to derive those statements. Modus ponens appears to be the answer for each. As I said before, you can also look at the end and work backwards. You just ask yourself, based on the nature of the conclusion, what could the last move be before the conclusion was formed? Since it is a conjunction introduction could be the answer. Reason backward as far as you can, step by step. You may be able to solve the whole derivation this way, or you may only make it one or two steps before you need to start working forward again. So, if we take this information that modus ponens can give us the atomic statements we need, and the conjunction introduction could be the last step before the conclusion, we can attack the derivation with a strategy. First, use the available premise A to break away the atomic statements that make up the target conclusion. In this first example, you can use line 1 and line 3 to conduct a conditional elimination with modus ponens, deriving B on line 4, and then the same thing on lines 2 and 3 to derive C on line 5. Now that we've worked forward from the beginning, we can move on to the next step in our strategy of working backwards from the conclusion. We know we want B and C, and we also know that B and C are valid inferences from the premises we started with. If we read the literal meaning of lines 4 and 5 out loud, we could say B is true and C is true. That should show us that the compound statement B and C is true. We just said it. Now that we know that B is true and C is true, we're justified in concluding B and C on line 6, and the derivation is complete. In Teller's next example, he introduces the concept of nested subderivations, but you won't be tested on these. The next couple of examples are intended to explain how to use the biconditional and the reductio. But since we won't be looking at the biconditional any more than we already have, and since we already explained the reductio, I'll just move on. Since recognizing primary operators, or main connectives as Teller calls them, has already been covered previously, and his explanations aren't quite clear in this chapter, I'll just be giving a brief treatment of his example. He asks us to prove that C is a valid inference. To do this, you need to identify the primary operator, that is, the one that operates on the whole statement. Another way you could think about this is, what was used last in constructing this statement? If you can't see it, Teller recommends attempting to build the compound statement yourself. We can see that in the statement, there are, in the first and last places, conditional statements, if A then B. These are constructed with the claim that if A is true, then B is true, and then enclosing them in parentheses. That's it for the first conditional, but the second is also part of a biconditional with C, so it needs to be connected with either a triple bar or a double arrow, and then enclosed in brackets. Once this is done, we can see that the last step is connecting them with an ampersand, making the overall compound statement a conjunction. Now that we know the primary operator, we know where we can start to prove the validity of C as a conclusion. The first thing we need to do is simplify the premise into its composite conjuncts on lines 2 and 3, using what Teller calls conjunction elimination, what I've been calling simplification. From there, we can use a rule that we haven't been using called biconditional elimination to set up a modus ponens on lines 2 and 4, and we can see that this is a valid inference. Our course of study only covers chapters 1 through 6 of Teller's logic primer, so this will be the last section we discuss. There are a few more chapters before it transitions to predicate calculus, but that's all beyond the scope of this course. Predicate calculus is nice, but not necessary for our purposes at this level. We only need basic logic for undergraduate college-level writing. Like Teller says, even though this is all difficult, with experience, all of this can become second nature to you. And when it does, you will be thinking logically. And that's the goal of this course.